короткое тире, и оно просто не запустится.
Раз, два. Все, я запись запустил, если что, просто руками выложу.
Хорошо, мне кажется просто, что доска...
Ну, а зачем доска, когда можно просто скопировать ключ?
Проблема в том, что...
Я сделаю, у меня целая
Ладно,
книга.
хорошо.
Ну, сейчас, давайте сначала проверим.
Понятно, все, есть порядок.
Есть? Да, трансляция?
Да, есть трансляция.
Спасибо большое.
То есть трансляция запущена, да?
Отлично.
Так, в конце потом завершить трансляцию вам нужно будет нажать.
А, в конце нужно
В конце,
просто...
да. В конце вот здесь остановить трансляцию.
Хорошо, хорошо.
И остановить запись, да. Ну, и закрыть просто программу.
Хорошо. Хорошо. Ага. Извините, просто как вы читали, наверное, кто болел и правильно как записать. Мне кажется, что не очень хорошо видно доска на видео, но это обычно. Каждый раз качество записания доски. So we have still, remember, we have a market, okay? So this is some new martingale, as we know. But the main example is DXT is some ether process, yeah? So is U of T and omega dt plus some V of T and omega dWt for W. It is just a quick recall. So this is a Brownian motion. These are predictable. Yeah, these are adapted processes, regular enough at times, say Cadillac, but this is a vector. What I mean? This is a matrix, right? And this is a vector. Okay, like we have our list of assets, x1, x2, x3. That's the drift of each of the assets. And this is the matrix that multiplies the parameter. So if you want in coordinates, it will be dxi t is ui at t omega dt plus the sum of j. That's what I mean. Aij, t omega. Let's just write. I never write omega. dwj. Okay. This was our typical example. We'll make some other example today. Maybe this I didn't discuss much. It's not a model I love particularly, but we can also think that xt is just what's called the binomial model. We have one stop, say one stop. So we started with some value 0 times 0, and at every time step, okay, it can say, let's say that we just can change two values. So we go up with some probability p. So from x0, after one step, we go up and say that the value will be ux0, or after one time step, we go down and the value is dx0. And then, again, with some probability p, we will go to u square x0, or ud x0 and d square x0. Yeah, and so on. Is it clear what I mean? Like every, I don't know, at every time step, you have a probability of going 2% up or 5% down.
Just a fixed
amount. Of course, you could fix, I don't know, 100 different values and not 2, but nothing changed. Okay, so in this case, u will be 1.02, d is 0.02. D was, let's say, 5% down, so 0.95, and that's this is obviously a martingale, yeah, because it's it even has bounded variation. Yeah, the value will be giving an omega. It's just in our space here. It's just giving a path here, and the path will be just some constant. And then you jump up, then you jump down, then you jump up. This is bounded variation. So well, it's obviously a martingale. This is called a binomial model. I don't like it particularly, but you can go good to check some examples. And this is a much more used model, class of models, again, even more generous than I apologize that that's our main example, and other example we will see will be very little more toward the end, but okay. Well, and then we had a final time origin t, okay, final time origin is possible, so it's just a final time. And we have f was a contingent contract, if you remember, contingent contract, which we should just interpret as a derivative asset. This just means, okay, sum of also f is just some random variable in L1, so the model is integrable. You can take bounds from below if you want, but the main thing is that f is measurable at time t. Okay, so what is the idea of this thing is that x, so beyond so in practice we just have a single martingale and a random variable, okay, mathematically. But what is the rationale behind what is the interpretation is that x is the value of all these assets. You can think that if you trade in Wall Street, x1 will be the value of Apple, x2 will be the value of Google, x3 will be the value of I don't know, Tesla, and all these stocks that are very fashionable right now, and so on. And f is what you want to buy, say, at time 0. So today, we want to buy f. That is some quantity that we will have at time t. Okay. Example, okay, who is f? F is a function of omega. We have a probability field, a probability space. I don't repeat it every time. F could be anything in this context. As an example, okay, is, I don't know, the stock 1 minus chi positive part. This is a function of omega, this is a function of omega. So that's, what does it mean in words? It means that this is the right to the positive part, to buy one share of the stock 1 at time t. So it's 1 at time t. I forgot to write. One share of the stock 1 at time t for the price k. Okay. So that if it is less than k, if the price of x1 is less than k, it's worth nothing. So it's 0. The positive part of something negative is 0. Because of course at time t you wouldn't buy for the price case if x1 is worth less than k, and otherwise you earn x1 at time t minus k. So in this example, t is called the maturity time, and k is called the strike price. But these are just words for this function, nothing special. That's called European option, right? So there are other types of options. That are more or less all included in this case, like well, less, not really, but for instance, Argent options, usually they are not the value of x content, that depends on the average of x over a period of time. Okay, so in this case would be some function of, I don't know, one, for instance, if the period is from now to then, 1 over t, the integral between 0 and t of x s dx. Another example. Okay, for instance, it could be this minus k positive part. There are some options that don't really fit in here. One is the American option. In American option, it's more like here you could have a function of t in this sense, but that's not really the point. So you have some function of time and omega. For instance, the value of x1 at time t, it could be not at time t, but at time t. But then what you buy is the right to choose the moment where to use this f. It means that the American option is f of a stopping time at omega. So what's the information more here and here is that you have the right to choose the stopping time. Is the theory argument reply is just the same every time with the web martingale you have to use martingale with the stopping time, but writing explicitly the value of the options, the fair value of the price of the options is a bit more complicated, and the optimal stopping theorem we will do toward the end. In any case, usually in this context, the basic fact is that you should never, the optimal tau will usually be t. Usually, with the final time. So in reality, I don't want to discuss it much because, except a certain number of situations that depends on when the companies pay the dividends and so on. Usually, the idea is that you should usually sell an American option as the maturity time. So tau should always be less than. But so this I don't discuss much. I don't know. There are the list of options. I don't know all the options that the type of option styles actually. I think of options that exist. I think there are Bermudan options. Bermudan options is like this, but tau is not that you choose. There are only a finite set of times. For instance, you can only sell the options or not at maturity time. Something that doesn't fit our framework is what's called evergreen options. And evergreen options, usually they have a very long maturity time, so they are evergreen, informally speaking, infinity. But also you need to announce that you exercise the option in advance. So like you tell to the bank, in 1 month I'm using the option. So when you announce it, so you see you have to use a stopping time, which there is a delay. So it's not only that tau should be a stopping time, but tau plus 1 month should be a stopping time. So this kind of, okay, of course you can make all variations, and I don't want to make a formalist for it. But let's stick to this case, which is, I think, the most usual, where the function is just measured by time t. Asian options are included. It doesn't mean that it's a function of x at the final time, even if this is the case where we will do kind of more concrete computations. It could be some function of the average, say, some kind of functional function of stocks. And of course, and this is not rare at all, it could depend on all the stocks, not just one. Okay.
Asian option is a function of omega.
A contingent contract is just a function of omega in L1. So, but what you buy is the right to exercise this option at time t. It just means that at time t you will have the value f. That's what we use when we define the buyer and seller price. So when you stick for the buyer or seller price for American option, you should also take a supreme or infimum over all the stopping time. Who tells me what was then the buy price for a contingent contract?
Expected value with respect to key measure of
The buy price, what was?
expected value with respect to
So this would be not exactly, no? This would be like, in what case would you buy the contract F? Okay. So if I buy F, okay. So at the beginning, suppose that there exists some constant y of this amount of money. Okay, at time 0, I give you y. So I want to buy an option from him. Okay, for what price? If he tells me for this price y, I will buy. If he tells me y, so I pay y to him. Then what I do, I trade on the market. That's the main point here. That there is a market in which I can trade. We are not just betting on. It's not just betting head or tail on a coin. We can trade on the market. Okay. So I on this market I trade, and this is so if I use the portfolio theta, if you remember, this is the change of the values of portfolio over time t. Okay, because t. You remember that V is just theta scalar x, but the portfolio is called self-enhancing if dV is theta dx. So if you want to consider just here, it's minus. And so this is what happens in the time of unity. But at time t, I have f. Okay. So if this thing, which is this is a constant, real number, how much money I have to give you. This is what I trade, and this is a function of omega. Okay. If this thing is positive, of course I will buy, because at the end I have something positive. So the buyer price, the maximal amount I'm willing to give will be the supremum of all the y's such that this is positive. The seller price, well, that's the same. He receives zeta, then he trades, but at the end he has to give me F. So if this is positive, he will sell for zeta, so the minimal zeta, such that this is positive will be the seller price. You remember this, yes?
And we take supremums and machines, not only.
Well, we take supremum because so I will be like the optimal buying price. I'm available to buy at this price or less. Okay.
At beta S somehow changes. We take supremum with the beta.
Sorry, I wrote it a bit too quickly. That the supremum of the y is such that there exists a T by self-financing. Yeah, you are right. Sorry, I was a bit too fast. B of F is the supreme of all the numbers y, such that there exists a self-financing portfolio theta, for which this is possible. And here also there exists theta self-financing. So the difference in an American auction is, a function of tau omega, and omega is also a function of omega. So it's not here the difference in the American auction, because last time somebody was asking toward it. It's just that here I also optimize our stopping times. Okay? T is not fixed as the stopping time. Nothing more, nothing less. The formulas then will be the same, just the concrete cases are different. So what we checked, okay? This we have defined last 2 times ago. So, but remember that we work under a general hypothesis that is the hypothesis that we always make. And this is experimental. This mathematical hypothesis comes just from observation of markets. And is the following: that there exists a probability measure Q equivalent to P such that X is a Q market, local Q market. I don't want to focus too much on local or not local, but Q market. This was slightly stronger assumption, but in the case that we consider it equivalent to asking that there is no arbitrage. I say it's an experimental hypothesis because mathematically, mathematically may admit arbitrage. What's wrong with that? Mathematically, nothing. But in practice, an arbitrage means that there is a way to make money for sure with probability 1, with strictly positive probability, with 0 risk, however, to sell, to lose anything. And nobody in the market will accept a strategy that instead loses something with positive probability without earning nothing. So it's a very natural hypothesis. It's a weak hypothesis. Usually one assumes much more. Okay? So in this case, we had that seller price is always less or equal than the expected value of Q with respect to this measure Q of F, which is less or equal than Q of F. So it's clear that if there is no arbitrage, the buying price and selling price will be ordered in this way. Because if somebody would buy for less than S, it means that I see somebody that sells, sorry, the opposite. S and B, I apologize. If it would be the opposite, okay? It means that I find somebody that buys at 100 and somebody that sells at 50. Okay, I buy from here 50, sell to him at 100, I make 50. That's a trivial arbitrage. This doesn't exist, okay? So the fact that there is this measure implies that B and S are ordered in this sense, because this values in the middle. If B and F would be, B would be strictly bigger than S, then there is an arbitrage. So this never happens. But then we also say that we have given this definition that a self-financing portfolio theta replicates if there exists a real number such that x plus, so x is like the initial value of your portfolio, 0t theta s dxs is f. And there was a slightly technical hypothesis was that this is marketable. It is a Q martingale. So X is a Q local martingale. So this is a martingale, a local martingale. Here we're asking, it's not just a local martingale, it's a martingale. It's also bounded from below, because theta is a self-financing portfolio, admissible in particular, but still, so it's a priori it's just a local martingale bounded from below, so it's a super martingale, blah blah. But we are asking that it's a Q martingale. So that, for example, if it's bounded, it's a Q martingale automatically because it's a local martingale. It's just like theta is not crazy big. I don't know what to say. Okay? If your portfolio is not allowed to be more than 10 billions of dollars, then it's okay. Okay, it's just a technical mathematical condition. It's not practical.
X is the amount of money we borrow before we start trading.
So, okay, this is just definition. X will like. You want to buy f, x is, okay, what will be at the end? X is just the average value of f under q, this quantity. But it's like theta is replicating it, at the time 0 you have x. So f admits a replicating portfolio theta, if at time 0 you have x, then you trade on the market and then at the end you have f. So for instance, I don't know, if f is f could be, give me you give me $10. Okay, it could be just, you give me $10. So x will be 10 and theta will be 0. Okay, so in this case, so if, and then we have just remarked, it was very simple. Yes? Remark if f admits replicating theta, then these are equalities. B of f is equal to S of f is equal to expected value q of f. So in this case, we say that this quantity B of f equal to S of f equals to S of f q of f is the fair price of the contract f. So the interpretation is the following. You go to the bank at time 0, you tell them, I want that at time t, I have f. F is measured by time t. So today I don't know what will be f in 1 year, okay? Big T is in 1 year. It's 1 year in the future. Today I want to buy 100 stocks of Google in 1 year, okay? At some given price, for instance. So I go today to the bank, and I tell them, I want this contract that I can use in 1 year, okay? So what, of course, this has a value, because I will give to me some money in 1 year, whatever, but today, in 1 year, I will have the right maybe to use it or not, okay, depends on f. F could be negative, S could be that I today receive the money, but say, as an example. So this is the price I should pay or receive from the bank today, the fair price, to buy this contract in the future. So it's a duty of the bank to quote me a price. And that's all assuming that there are no transaction costs and this is and that this is a fair model for the market. This is the only price at which I will be interested in buying, at which the bank will be interested in selling, and which is fair, okay, which will not allow to any of us to make an arbitrage. Because I mean, if it's if they sell me for less, then I replicate it theta, and I take if the seller has value x, I will earn x minus expected value of f minus x. So I will make some free money. So this is what we checked last time, and then we were trying to understand. Okay, but in practice, what does it mean? Okay.
So we should simulate our stock prices, simulate F, and with respect to risk interval.
I mean, in some sense, this is let's first do recall general fact, and then let's try to specify what happens in some cases. Okay? So suppose I have xt is, if you remember, semi-market is always the sum of something with bound variation plus a local market. What would be the temptation here to make it? We have to. This is okay. This is a. We have our property measure p. This is the real law of what our market does in the future. Okay? The real probability measure. Let's think p. The p word. Then we try to build. So there is we are assuming that there is this cube, but in practice, if we want to price f, we need to find this cube because we have to respect values of the cube. The idea is to try q in the form exponential of some stochastic integral with respect to n. I prefer to call it psi, maybe keep this thing dxs, and then also p. In the sense that this is the random negative derivative of this probability measure with respect to this. This is stochastic exponential, is positive, and so it's, these two are equivalent. Of course, will this be a probability measure? Well, this is a local marking, good chances, but you remember the expected value could be less than 1. So there is this is okay if, so okay means that is a probability measure if the expected value p of the exponential, let's say of 1/2 the integral between 0 and t of c s squared and dxs is finite. But this is again, you should always distinguish what's the so there are some technical things that are kind of technical. This is a technical condition. We know that this is a local market, and I say, oh, it should be a brilliant market. Okay? The same is here. This is just the expected value of this guy could be less than 1 if C is sort of too big. So this red is a technical hypothesis, okay? If you implement something on your computer, it's not that infinity will arrive ever, okay? So these things are technical hypotheses to make the mathematical theory work. Again, when you implement something and then numbers are so big, you will have a simulation instability. Machine precision will be has to be checked, but okay, these are little nuances. That's not the key. Okay? So this is how we search for the equivalent probability measure. Then Girsano's theorem tells us that so this with Girsano, it tells us that that mt minus the cross quadratic variation between C and M, between the minus the integral between 0 and t of Cs in the xs and s, but cross quadratic variation is a mapping. You remember we proved Girsanov in full generality. If you make an equivalent change of probabilities and martingale, there are some martingale, this we already knew. And if is this clear? You want me to go a bit to repeat this part?
Can you repeat?
Yes. So in general,
Why did you use Girsanov? For what?
so you remember the Girsanov theorem told us several things actually, no? That if they store a probability measure on same equator probability space, there is a martingale which is positive, which is equivalent, it rises an exponential of some martingale. Conversely, if I make the exponential of some martingale, okay, provided that the expected value is 1 not less than 1, so provided that this martingale is not too big, this will be a probability measure. Okay. But the main point, so if Q is expected value of some martingale NT P, and M is a P martingale, this was the theorem, Girsanov. He was just a young mathematician just in Lomonosov, who died very young in mountain accident. If P is then M minus the cross quadratic variation in M is a Q martingale. The example to keep in mind is that we have dx is u dt plus v dwt. We take nt equal to integral between 0 and t of cs dws. Then W was a P martingale. Then NT, sorry, then WT minus the cross quadratic variation between WT and NT. WT. But who is this cross quadratic variation? This cross quadratic variation is the integral of Cs in dx. So this function of t and omega is a Q martingale. That's the theorem. So if we call this WT tilde, this is an example. Example. Okay. If I call WT tilde these things, WT minus the integral of psi s ds, dx will be u dt plus v dwt, and that's equal to u plus psi plus b psi dt plus v dw tilde t. dw tilde is dw minus psi dt. This is source of a lot of confusion sometimes for people. This equality, P and Q are equivalent. So this is true. Both for P and Q, these are just identity, I'm not sure. Just This is a P Brownian motion. Under P, this process is a Brownian motion. And this is a Q Brownian motion. Okay, that's the Girsano's theorem. So if X solved this, had this law under P, X has this law, and this is a Brownian motion under Q. In particular, if I choose B such that I choose Xi, so Xi equal to minus Xi solves this linear equation. This is a matrix, this is a vector, this is a vector. If I solve, think that everything is scalar, right? This is number, I divide Xi is U divided by V. You see that X becomes a Q martingale, because the integral of V in dw is a local martingale. So that's what we are trying, that's the idea. If this is my market under the real P, the real probability measure P, I make a change of variable through an exponential martingale. If I choose the right side, X will be a Q martingale. X is what it is. I don't change it. X is a function of T and omega. It's the value of actual stocks, okay? X time T is the value of the actual stock time T is T. But if I change the Q, if I change the probability measure, the distribution of X changes. The law of X changes. I just, to price options, to price derivatives, I just need to find that measure that makes X a martingale. There is basically, Girsano tells us that there is only one way to do it, and is to do an exponential change of measure, so to write the Radon-Nicolin derivative as a stochastic exponential of and then it also tells us how the process changes under this change of measure. So who stays a mark? Who are the martingales? New martingales are old martingales minus this cross-quadratic variation of exactly the density and the original martingales. So what we did here for the process is this was the example. We can do it in general if you want. Okay? Just because every semi-martingale just is the composition. So we do exactly the same. We try an exponential change of measure in this Girsano form with a stochastic integral with respect to dx. Just there are a bit of these red technical things that this is not necessarily a martingale, this exponential. Okay, it's just a local mark. But okay, if some integrals is fine and if things are not too big, it will be an exponential. So just you see what we look for then. Okay, we look for psi. So when this our hypothesis, the existence of an equivalent martingale measure, risk-free measure, will exist if AT is of the form. So let's write this DAT. So back here. So the lack of space is even more critical than usual. The market, so remark. Here, the market xt equal to AT plus MT. This is BB, and this is a martingale. Admits a local, an equivalent martingale measure. This just means probability measure Q, such that X is a local martingale. Q. If dA is equal to psi t dx6 for some psi such that, however, the expected value of E the 1/2 the integral of 2 t psi squared dxs s is If this is, then you make the martingale measure. Yes, it's a. As it is written, it's fair. I need to indeed, let me finish it. So that it will be. There is a mindset case business, indeed. Just take Q, the exponential martingale is, this means exponential of integral GDP of sizes. Also, I recall you, right, that if x is a log of the martingale, the exponential, no, it is actually the same. The exponential of x was defined as the process. If y is the same, if x is the same martingale, y, the expression of x, was just defined by the relation that y times 0 is 1, and by is y over t is yt, b is t. We check that this problem is a unique solution, and this solution arises as yt is actually the exponential of xt minus 1/2 x6t if it's continuous, and more in general, here was a product of the less than t of 1 plus delta xs e to the 1 x. Okay, this is just an explicit expression, but that's the.
Inside of exponential we have upbound small t, like here. No. Q equals exponential of some process and some.
No, so you can write like this. I don't mind, but what it means of. I mean, this is not a function. So if I write like this, it looks like it's a function of this quantity, but it's a function of the whole process. You see.
Okay. So we can just write small t in the upper bound in the integral.
Here.
Yes, small t. So it's like some process.
Yeah, but it is this process. But then so if I give a process, it's a martingale. You can make a new process, which is this exponential, and then you compute the time t.
Okay.
But this is not a function. What I mean, it's not a function of this at time t. You see, you cannot write all this. If you want this at time t, okay, y at time big t. Okay, here there is x at time t. But here, the quadratic variation depends on all the history of x up to time t. These things depends on all the history of x up to time t. It's not a x at time t is not a real function of x in the scale at time t. Y at time t is not the okay. So you give me the process, I can make the exponential. But if I only know the process at one time, I cannot make the exponential up to that time. It's that process is a function of the whole process. It's not that each time it only depends on the process. Depends on the process up to that time. Okay, but in case this Ito case, we should really keep it in mind. Okay? And then, once we build this, then you give me F. So, of course, one would like to write anything. Can I erase? If you have questions, ask them, because that's a good moment. It's a bit complicated, okay? It is a bit complicated. We have something which is just a semi-martingale, we make a change of probability measure, we get it. The process stays the same, but it's logic. Being a martingale is not a property of x. is a property of the probability measure on which you deviate. So it's a classical problem. In general, in probability, you want to find probability measures such that certain things are marked. Markov processes usually are characterized in just progress. Can I erase? So, for instance, okay, you give dx with u dt plus b equal to t. We will try to be more explicit, much more explicit today. But okay. And then this is our market, and this is f. You want to find the third price for f. Okay. Very well. What do you have to do? Step one. So price. Find. This is the market and this is the problem. Find. Let's do this. Problem. This is the market. So a model of the market first. And the problem is find the third price of the contingent contract F. What do we have to do? Solution. 1. Find psi. I don't remember if last time we called it psi, I'm sorry. Find psi. So this is psi, which will be a function of s and omega, because all these things are functions of time and omega, such that v psi is u. The technical hypothesis, I write it in red, just to remember that this is a little nothing in some sense, to check that the expected value of e, the 1/2, the integral between 0 and t of c t squared t is finite.
Minus mu.
Okay, I will put the max in the exponential, or you can put it here, psi. If psi has this property, minus psi has this property. Yes, I'm sorry, the sign. I'm being consistent. I mean, the formulas are correct, but consistent. And 3. B of f equal to q of f. This will be just the expected value with respect to q of f.
You mean the center of mass.
Oh, thanks. And this will be just the expected value of f with respect, if you want to write the expected value with respect to p, which is not necessary. So q is p of c. So this will be so that times e to the minus integral between 0 and t of cs d ws minus 1/2 integral between 0 and t of cs squared. Actually, if you want to compute it, we will see in a moment that this expression is actually, it could be more useful. Because if f is a function of x, okay, so with W tilde equal to W minus integral incident T psi s yes, X will be VTW tilde. That's why it's a Q minus. So if f is a function of x, you're just taking an expected value of something that, I mean, this is actually the expected value with respect to W tilde. Okay, you're just basically just means. Still, this looks still a bit who is U, V, and so on. Okay, but let's make a very practical example, which is what people use for good to integers. Naive as more, but it's like you want to so you go to the example. In this example, which is probably what you have to do if you work as a quantitative analyst, it's not that you will have you will not have enough money to go to the bank and trade this big quantity so that you get quotes on options and so on. Okay, it's explicitly done for you. It's the opposite. You should think that you are from the side of the bank and there's a customer coming. Okay. So somebody comes and tells you that's what happened. And now things are a bit more sophisticated. But somebody would come and tells, I want to buy this amount of dollars in 1 year for this price, okay, or this stock in 1 year for this price. So what you would do, okay, is this asset, this x, one dimension. Let's say the first component, x1. Cool. What do? You take the simplest possible model. dx1 is alpha dt plus beta dwt. Alpha and beta are constants. Who are these constants? How do you guess these constants? Oh, well, you just check. Sorry, I forgot. Everything is linear here. Beta is 1. It's very natural that you put so. How much x changes? There is a drift which is proportional to x1, and there is a volatility which is also, and then again, how much it fluctuates is also proportional to x1. This is very natural. You cannot expect it. I don't know if you measure the stocks, the value of the stock of the asset in dollars, or you measure the value of the stock of the asset in cents, so 100 of a dollar, the final model should be the same, isn't it? Okay, so the bigger is the value, the more like it fluctuates. Okay, the alpha and beta should be consistent with the unit of measure that we use for x. So, of course, it's a very simple linear model, but it's the simplest thing you can do. So who are alpha and beta? Well, you have the data, what the stock did in the last, well, this is a bit up to you. What is the relevant period of time for this stock? Okay. Well, of course, maybe if you want to do in 1 year, maybe you should more or less understand how the stocks behave over the years. If you want to buy the maturity time will be in 1 week, maybe you will use a shorter period of time to really catch how X behaved in the last weeks. But you just take the historical series of values of X, okay, and you estimate from it alpha and beta. I will give it so. This simple model you can do as an exercise, okay? There are plenty of libraries to download historical data from the internet for free, okay? If you use Python, there is Pandas data reader, or you can use Y-Finance, the library of Yahoo, Y-Finance. Bloomberg also has its library. I don't remember the name, but maybe you have to pay to access. Maybe they have a very strong layer. These libraries usually have a bit of delay. Like you can download the data up to 30 minutes ago. If you want to download real-time data, maybe they will ask you some. The service in Yahoo will ask you some money. Pandas, of course, it's open source. But of course, pandas will use, I think pandas actually use this Yahoo as a database. So it's free, but of course you don't find the last 1 hour of data, but that's absolutely, we absolutely don't care. So what you do, you download the data, and you try to estimate from this data who is alpha and who is beta.
I think that beta is estimated via the price of options itself, because there is so this would be historical volatility, but I think implied volatility is better for.
You are perfectly right, but yes, but even now this is not what you would do. This is also it's a simple linear model that has been used for a long time in the stock market, but not since kind of modern computers appeared on the scene. Okay? So okay, but this is okay. You estimate alpha and betas from the data. If you download the data of the stocks, if you only have data of the stock X, okay, this is your task maybe to imagine one of the many ways to estimate alpha and beta. But it's clear that you can get a reasonable estimate. So, no, beta will depend on how the change of X varies. And that is just the average on one step of other change. Okay, so look, we have, let's say that from the historical data, we estimate alpha and beta. But then, if you, of course, if you have other data, of course you can use them. And this is an idea not just for markets. This is like even if you are just a financial consultant, even not for assets. Even somebody asks you estimate of the price of. Some factory, the company wants to buy a factory somewhere in the world, and they ask you, they ask to your company to give a rough estimate of the value, even just for fiscal purposes. And then, what's the main reference to value something is how it was valued in the past, how somebody else did it. That's the main reference before you. So that's your starting point, and you can do some. Then basically, how financial companies that this thing is working, they take what was in the past and they take what the customer wants, because who asks for a quote of the price is who pays you, and then they just do some mathematics to glue what was in the past to what the customer wants. It's not very kind of ethical behavior, but this is very, very, very wise strategy. So. But this is okay. So, but what you claim is absolutely correct. So, the main reference to estimate something is what has been done in the past. Of course, it's not like you're right, and because some formula tells you the price which is completely off, but then you really believe it. So, you're right. But this is not our result. Okay, we take the data, we estimate alpha and beta. Cool. Then, okay, here it is very easy to find V xi equal to U. V is alpha x1, beta x1. U is alpha x1, psi is alpha divided by beta. Psi is alpha divided by beta. B is beta x1. B is a function of k and omega in general. In this example, it's just a constant time x. Oh, let's put the one upstairs so it doesn't matter. It's one t and U is alpha. So U is alpha x1 beta. I was looking for a function such that big psi is U. So psi is alpha divided by beta.
So in this case, we easily take this C because I can be constant.
Yes. Well, if it was, but also mostly because, okay, this is just scalar, so there's just one, our market is composed by one asset, of course, of simplification. Otherwise, this would be a matrix, and you have to convert, and so on. But then also, this is x1, and this is x1, so one is numerator and denominator, so just add the by beta. And then, okay, and let's say that f is some function of x1 at time t as well. F of omega, this is very typical, okay? It's a European, this is a European quantity. Time 1, maybe under the time of the resolution. Oh, but x1, now x1t is just beta x1t dwt, where wt is a cube Brownian motion. And of course, at time 0, you know that x1 at time 0 is a small x. Now, this simple problem has the nice feature that we can find the solution explicitly. x1t, who will it be? It will be small x. Okay, this is just, no, yes, this is small x, e to the beta w tilde t minus 1 half beta square t, if I'm not mistaken. What? It was just the stochastic exponential of beta w t. Initial value is not 1, it's x. Okay, so the surprise of our function of x1 at time t is the expected value with respect to q of value times 0 e x or f of x e to the beta w tilde t minus 1 half beta square t. This is a cube Brownian motion. This is nothing weird. I can write it as a normal integral. This is just a Brownian motion. And only at time t enters this formula. So this is just 1 over square root of 2 pi t, the integral between minus infinity and infinity in the z, let's call it, of f. Okay, it's like you should take this minus k positive part, or is the favorite function. F in x e to the beta z minus 1 half beta square t. And then the reduction density, e to the minus z square divided by 2. Is a function of a Gaussian random variable of variance t. So I got a very explicit form. I consider, so usually now you should consider also the inflation. Now there is a second x0. We always taken the safe asset constant. Yeah, no, just otherwise, just you should just discount the value of money with inflation. So You should divide by the vertex. There is a little modification. You should divide by the final time of x0, and here you should count a time and the value you count. But it's let's say that it's not. So with this formula, this is now very explicit. Okay, this is what you dream of. You know the model is simple. I took a linear model, but then I just came with an integral, which you give to Mathematica or Python or any numerical. So you give to your computer, and it computes. Until probably the 80s or even 90s, when f was exactly f of y, let's say, was exactly y minus k positive part. On Texas Instrument scientific calculators for traders in Wall Street, there was a button, okay, where you entered beta, k, p, and they give you this number for this function f. You know, there was plus, minus, divide, multiply, square root, and the Black-Scholes, you understand the calculation. You are too young, but I really told you, when I was younger, we had calculators, you know, that could, there was no computer, but maybe you could plot a graph on some more advanced calculators. And one of the buttons on this more advanced calculator for people operating on the market had this formula. Because it's just a linear model, but otherwise, what do you do? It's not solved. How to price notes, and this, okay, in reality, you reduce it even more. You reduce this to, in this special case, you can, okay, just make a change of variable over t and just reduce the standard reduction because it's not. I don't know if this surprises you or not. It should not, but of course it does. This doesn't depend on alpha. The fair price of this option doesn't depend on alpha. Okay. In your model, you can just estimate. If you want to edge these, you should know alpha, but otherwise. So it's quite surprising. Okay, if you want, you go to the bank. There are two stocks, Apple and Google. The last relevant time of period, Apple increased with the drift alpha very big, and Google with alpha very small. One is growing much more. Okay, but if you want to buy Google or Apple, today they have the same value, say X. But if in 1 year you want to buy today the rights to buy Google or Apple in 1 year at $100, the price of this option or the price of this derivative will be the same. Even if if you look at the model, in 1 year Apple will be much more valuable, and so depending if you're putting or and so like the probability that it exceeds $100 is completely different from the one of Google. But that's not relevant, because you could, if you buy at a different price, you could in the meantime trade on the market and get it for the same, just because today they're the same price. So actually here, alpha may not be constant, it may actually be random the way you want.
So you will have this fy function, just
F here is anything measurable, of course, such that is expected to very finite, but is there any function? This is a classical
So in this classical case,
This is just a classical call option.
so we just get but
Yes, this is just the classical Black-Scholes formula, but I mean
in Black-Scholes formula we have risk as
Risk-free what?
so the risk-free measure is Q. What's called the risk-free measure is Q.
yeah.
But in this simple linear case, so what's special here? That I could write x very explicitly. Okay, I found the solution x very explicitly, and then I know the law of the Brownian motion, and I wrote it as a Gaussian integral. This, of course, is absolutely special of this linear case. I was a bit quick here, and probably I didn't stress enough that this is true because we can edge the claim. We can edge is the same as replicate. We can replicate F. There is a replicating portfolio, admissible replicating differential portfolio theta, such that the case you remember this. Yeah, we recall this tree. There is a general inequality. It's an equality that exists. We have seen it last time. That if we can invert this, as in this case, then we can edge. But so we find the portfolio. But let's check it. Let's then check it more in detail. So yeah, the problem we discussed really details. The problem. Then we will make again a concrete example that will clear things a bit. The problem of replicating quantities. Because yeah, what we calculated is this. We calculated the expected value on the Q of F. But we will find, will there exist a replicating portfolio, or this a priori may stay in inequality? So, how we edge, you have F, how do you edge F? How do you find a admissible portfolio? Such that theta, such that F, sorry, set transport portfolio theta, such that F writes as integral of theta S and xs. That's how to find theta, if it exists. Theta, if it exists. And this is in general a difficult problem. There are some techniques using Mallavan calculus, but it's a bit delicate. Paul Mallavan was a very famous French mathematician who passed away in 1980. There are a lot of applications. He sort of invented some geometric version of stochastic calculus, which is particularly used in finance. Yes.
Can our data just contains another conjugate? For example, if we use conjugate like an acid.
So theta, you remember, theta is any. So theta, it should be called like that, no? But it's just how much is theta zero? It's included, but here I will just command. How much units you have of each asset? Thank you. That's your choice. It's your portfolio.
So, for example, I have 3 conjugates.
Yeah, but it's a function. If you want, you can take only. We are thinking that you can buy any amount. Okay, also 0.0001. But it could be also just integers. If you can do with integers, number is perfect. But it's like it's evolving over time. Like of the stock one, I take this amount, then I sell some. Or in principle, what you're thinking is that you can change also continuity. And this is what I have over time on one. This is my strategy. This is what I do. And theta of the value 2, that's what I do. And of the value 3, that's what I do. But at each, when they are adapted, each time t, it may depend on what x does up to time t. Usually just at time t. So theta, yes, is a function of x, of course. But theta t, so theta is a function of omega. So it can, at time t, it can be some function that depends on t of x, for instance, up to time t. For instance, if your property space has other things, so x maybe is just your stock, but maybe you know more things. I don't know. Space, I don't know. And the oil price, which was not one of the things that is traded on your stock, on your market. So nobody forces on theta to be just a function of x. But of course, it cannot. So it's on a filtered space. Theta t is measurable at time t, which is kind of mathematical way of saying that what you choose to do can depend on what happened up to time t. You don't look into the future. Did I answer your question? So yeah, it can be a function of other things of x in this sense, yes. But I don't know. It's not a contract. It's not some. It's what you do. Theta is what you do, or your customer, if you're a bank, do. But like what the agent on the market is the portfolio. So cool. So what is the general strategy and what happens, at least in some cases? For instance, this burning function. Case for binomial model that is so you remember, if you have a martingale, so we have our market X. This is the same martingale, but it will be a Q market, local market. Local Q market. X, the market, is just a vector of stochastic processes, is a local Q market. And then you remember that if we have a local, let's say, martingale, MT, if I have MT is another martingale, this is two martingale. Then we can write MT is an integral with respect to x plus a remainder with Lx as zero cross-correlated variation with respect to. We proved this thing last time. If I have a martingale, local martingale, and another martingale, there is a sort of orthogonal decomposition in the sense of quadratic variation. It tries a stochastic integral plus a remainder. This is the remainder as cross-quadratic variation. And actually, we have checked that if x is this is a Brownian motion, for instance. This and this is measurable in the same sigma algebra, and this is constant. Or more generally, that L, if x is a Brownian motion, respective value of L given P is a cross of the iteration of Brownian motion, US is constant. So you see that if our market is large enough, or in any case, if so when we want to, how do we want to apply this to find so we are trying to solve the problem of replicating content. So this is a recall. No, here, recall, yes. This is we have seen last time. So recall this, okay, this fact. Every martingale writes in this group. So maybe that m and x have nothing to do with each other, their cross-quadratic variation is 0, then x is 0. Of course, the remainder is m. But you can sort of project a bit along the things that are integral of x and so how do we apply this? You give me the contract f, I take nt, the expected value of f given ft, under q. This is a Q marking. If you fix an integral with random variable and you condition at nt, of course it's just the Tower property of conditional expectation. You condition at nt and the condition at ms is the value at nt. Okay, expected value q over mt given fs. This is expected value q or expected value q of f given ft given fs. And this is exactly the expected value at the smaller time, so it's ms. So this is a mark. Q mark. Now, if m, so I apply this decomposition theory to mt. Mt is equal to, or the final time, mt is equal to some lt plus integral between 0 and t of some psi s and dxx.
What you said
I applied, mt is a marker, I apply this theorem.
okay.
At time big T. Now, yeah, maybe I should write a bit more. My problem is that since I speak Russian so poorly, I lost a bit of habit of writing things, words on the blackboard, because otherwise I have to write them in Russian. And so maybe if you want, I try to type a bit more. No, it's okay. But I say things, but I don't write everything. So mt is the expected value of f at time with respect to ft. F is measurable, and t is nothing but f. And this, I'd like to take psi equal to exactly theta. If I take, I mean, then let's be. I try a bit, but I can always write f in this way. If, however, if Lt is a number, is a constant, namely does not depend on omega, does not depend on omega. That was the case, for instance, when x was a Brownian motion, and f was measurable in the integration of the Brownian motion. If Lt is in R, so now if the contracts have this property that this remainder is just a constant and is not depends on omega, that's a property of the market. If you want that every contract as this can be written in this way, for instance, the market was Brownian motion, it's fine. In general, however, it's property of f and x. But say there are many such contracts. Say like I don't know, if this contract depends only on x, then kind of even x is a fair marking, you can expect that this is the case. This contract is not too exotic. It's not a crazy hypothesis. It's something which is true in many cases. That this remainder is just a constant. So the R does not depend on omega. If this is a constant, then take theta equal psi. Remember that changing theta 0 can always make a portfolio self-financing. Just take what is not self-financing, I take that I use the mark. This is just C1 x1 plus x2 dx2, C3 dx3. There is no x0. We decide this notation. Then we just forget about self-financing. So we found our so when can we find such a replicating portfolio? Well, every time this remainder is constant. Constant in the sense that it's not random. So in principle, completely in principle, if it's random, it's not that big problem. It's random, but it's kind of orthogonal to x. So I don't know how to say. You go to the bank today and you want to buy the contract F. Okay, this to replicate F, you have this part, but this is a random in the sense that depends on things that have nothing to do with x. Okay, I don't know. This is Apple, and if you really would like here a constant, well, you would need the oil price. Okay, in your model. Of course, it's just a model. But then, okay, in principle, you go to the bank and tell them, I pay you this money today, and then, okay, in 1 year, when I buy Apple, I also compensate depending on the oil price. I don't know how to say, it's a bit, like the amount of money that you need to give at the beginning is not constant, it's random, but it's also random, okay? So you make a contract times 0 that, no, I give you LT of omega in general. It's a bit unusual, but in principle, that's what you should do to make the theory work all the time. Okay, this can also be random, but it should be interpreted as much less random than F. Here you absorb all the randomness coming from X, and here is this remainder. Now, if the contract is such that all this randomness is coming from X, let's put it in this way, then this is a constant, and that's what you have to pay the option. What you have to pay your cost. Otherwise, in general, this is random, and okay, it works like that. What can we do? But okay, so this is the idea. So just write F as a stochastic integral. We have for Brownian motion. You can do stochastic integral for this, and let's and this is how to replicate. And in this case, then this constant LT will be exactly the third price. If this is a constant, it can only be. Then takes it, and it's good to remark this. This constant is just the expected value under Q of F. It's just the third price. So because if I take the expected value, this is expected under Q. This is a mathematical expected value is 0, and this is expected value.
Randomness in LT could come from F or
yeah, I don't know. For instance, the market is Wall Street, Apple, Google, and so on. And we make a contract that is at time t, I throw dice, and you give me as many euros as the result of the dice. How do you compensate for it? Trading in Wall Street, there is no way. You cannot replicate the result of my dice. So of course it cannot be true that any here is always constant. Mm-hmm. But let's check in what cases. So if F, on the other hand, if for instance X is a Brownian motion and F is measurable in the filtration of Brownian motion, then L was a constant. This we checked last time. This is exponential. It was a bit tricky proof. Yeah, remember example. Yeah, example. If example. If F is measurable, so let's say that F is some function of a Brownian motion S in the dimension up to time t. It's a function of the whole instant. Okay, it just means that it's measured at time t in the filtration of Brownian motion. Then, and of course it's integrable, which was one of the hypotheses of that. Then F, then there exists a constant, which is just the expected value of F. I call it Q. Such that F is X plus the integral between 0 and t of some theta s. Now let's go excited. That's what we checked last time. Every marking, like I write like this, so the final time we just have, in this case. Every marking I write like this. But if this is measurable in the sigmatic generated by the Brownian motion, another sigmatic Brownian motion, this is a constant. Because this is cross quadratic variation 0 with the Brownian motion, and so on. So it's again, you need to be measurable and systematic generated by the Brownian motion. If this is Tesla stocks and I throw head and tail the coin, there's nothing to do. You can.
In this example, our market is also modeled by Brownian motion.
So okay, yeah, so let's not complete. So for instance, the x could be u dt plus b dwt. Okay. So there is x is not wt, is a equal process.
So v could be a process.
Yeah, these are processes. Yeah. These are stochastic processes. But then another example. Okay, the x is this. But with I don't know how we call it. And there exists L, say, some process LT, such that UT is ET exists LT, such that UT is ET LT, and the value of P is 100 that. Then we get Q. This was the basic hypothesis. And X. And so that the X is dt v w tilde t, and w tilde t, which is just wt minus plus dt at t. Is a Brownian motion. This is the part of existence of equivalent Martin. This X is a local of Q. Cool. Then what we do here? F. Then we write. Then if F is measurable, sigma filtrate up to 20. We write F. We know that F writes as its expected value plus the integral between 0 and t so x and dw tilde s for sine s, and we choose dt so that It's V plus the integral of theta s v dw tilde s, namely dxs. You see, this is a matrix, so this I can, if f is measurable with the sigma algebra, this I can always do. But then if v is not invertible, maybe that this theta doesn't exist, and maybe I cannot have the claim. So it's not completely automatic that, the fact that Q exists, so that this is the point, the fact that Q, equivalent mathematical method exists, it's always true. Let's say it's a very, very weak hypothesis that is always, otherwise there is an error, basically, almost. But it doesn't mean that we can edge any claim, even if it's measurable with respect to the Brownian motion. But it's obvious if this is not, again, if this is not measurable, if this has a lot of zeros, this B, some directions are not in the span of this matrix B, there is no way to replicate those directions. How to say? We have x3, x1, x2. They are all fair. They are all fair stocks. But x3 has nothing to do with them, and there is no Brownian motion here. Plus 0. This has its own Brownian motion. Maybe this has its own Brownian motion. This has its own Brownian motion. How do you cannot kind of replicate something from here easily, because this V will not be invertible. Okay? So if F writes as C3 dW3, you are in trouble. But it's more delicate. For instance, it could be that x1 and x2 they have the same Brownian motion, but there is no W2. So they have two stocks with just one Brownian motion in the model. There is not enough directions to replicate functions on x1 and x2. It's just from here. Because in this case, who will beat V? You can think that you have W1 and W2, but V is like 1, 0, 1, 0. It's not invertible. Okay, here there will be V11 W1 plus V12 W2, but there is 0. This is not invertible, you cannot edge. So, depends. Some claims you can edge, but not any of them. You take xi, which is not in the image of V, on the left. There is no way to edge that.
Excuse me.
We will see a more very practical case. And when it's time to get breakfast, maybe. Oh.
Yes.
Late. Okay. Let's take a break, Houston, and ask the person during the break. Какие что
It's about exercise 4, it's philosophical, so, but somehow, what is the possible answer? So this reflects that XS is our portfolio and DY and YS is somehow market.
Yeah, for instance, yeah, this is the, or even just in this kind of, yeah, yeah, that's good. I was thinking also, yeah, but that's even better. Plus sigma or p, we wrote today p dw, and this is like within there is some driving noise that causes randomness in our market, and how our stock feels it is not anticipated. It's v at time t times the increment, that's the v plus delta t, and not. So it's, yeah, because like this is what you see at time t, and like if you make a discrete approximation, this is a bit the rough idea.
This explains why we need to be eating integrals.
Yeah, I don't know, something like this or any word there.
Okay. And so
it was explicitly done in a paper. It will not be like this. Okay,
and
I don't remember what it was. I had some questions. The answer was that your boss will fire you.
your boss
will fire you. I don't remember what it was.
So the stochastic integrals we needed to reflect what we can gain on the market, right? By changing.
But you know, your example is like X is your portfolio, Y is the change in the asset value, and this is the change in the
portfolio
value. That's a good. I think. I know one of the things is what you have to do at home. One of the studies.
Exercise 9, I think.
Yeah, this is what we do today. That's why we have to postpone. Goodness, yeah, we have 1 hour. Let's do it. Yeah.
Sorry, I just another course.
Okay. Yeah, maybe this. It's not unlikely that there will be something about what we do in the last hour, because it's also an example, so you can check the video.
Yeah.
I don't know how many people wants to do the exam. You were one?
I think maybe 7 people.
That's good enough. Then we do.
It's a rough estimate because I think at least one person
It's good. I prefer it at least a few people. But if just very few people, very, very few, I would give some extra work and you could present small, it's an article or something. If it's people from masters, one person is from PhD, or we could do something. But if it's 7, then it's too much. So,
too much, right?
Students will have to listen to. So it's something where everybody needs to listen. You understand? It's like you present an article, for instance.
Okay.
But then 7 articles, people will should start in the head. But it's in reality it's better. 7 is better. See, many people that are students are not in Moscow, a lot of online. And it's for the education is a bit. I mean, I understand, but
I think maybe it's a little more, maybe
huh?
I think a little bit more students would like to take maybe a 8 or 10 because some of them do not attend the lectures.
Okay, this is, we start back, so this is still a bit abstract, okay, because, yeah, f writes in this way with some psi, and then okay, this is just linear equation, okay, nothing bad. But okay, I give you f, how do you write this is an integral? With the psi, it's not clear, it's not constructive what we did. You remember how we proved the existence of this psi. We say that basically exponential martingale built from Brownian motion span L2. This was the proof, basically. So, I mean, if you go deeper in the question, psi will rise as some Maillard derivative. But I give you f is the value of a stock. Do you find psi is not obvious, and indeed in full generality is not obvious. But we have seen, for instance, that for this model, for this Black-Scholes model, dx equal to alpha x dt plus beta x dwt. In this case, we have found. In this case, everything was explicit. So let's check a very important case, which is crucial, which is the case where the market is a Markov process. Not only saying market, but a Markov process. And since it's quite important, I would do a bit the opposite of what I did before. Let's start from a clear example, and then let's comment a bit on the general. So let's. In reality, up to now, I was just recalling what I do very often, adding a bit of information what we did last time. So that's the new part. In reality, we started quite late, but it's a new part. So let's call it. Let's call it lemma first. Okay, lemma 1. Let dx equal to some okay, it's a vector if you want, but some function of x dt plus some matrix that depends on x dwt. So this is a special case of Benito process. Okay, here we do any u of t and omega, any b of t and omega. Here, this vector and this matrix are functions of x itself. But in reality, this is a very, except that here you can have other marking and unstudied Brownian motion, this is a very general model because this is what is there at the end of the day is a Ida process which is also a Markov process. Because very often when you have a process which is not Markov, okay, maybe x1 is not Markov because it also depends on other things that doesn't make it Markov. There's some memory or something. You add other components and the whole vector will become Markov. Adding enough information to the space, you can make a process which is not Markov, a process which is Markov. So let's consider this case. Yes. We have into formula, right? So then f for each smooth function, f of xt minus f of x0 minus the integral between 0 and t of b of xs df of xs. Let's make differentials df of xs ds minus 1/2. So if you remember here is one integral between 0 and t. If you want to write the multidimensional form, it would be like sigma square f second. But if I write the multidimensional formula, here if you remember there is the trace of sigma joint of xs action of f xs ds, and then there is the martingale term. So let's say with an equal, not minus, but equal this plus, or maybe it was nice as a word, minus. And all this is equal to integral between 0 and t of df of xs sigma of xs dws. Except this, it's all normal, dx, yeah? If dx is b dt plus sigma dwt, then the increment of f, so once I integrate, df is b, is df, the differential of f, dx, so b. d sigma dv df. Is these two together are just df of xx and dxx. Yeah, when I do then dx is then b dt, it's here, and plus sigma dwt is here. The special term is this eta term. You remember we proved the eta formula for general semi-marginal. Here you would have the quadratic variations and jump parts, but the motion is continuous, so there's no jump. So this special thing is due to the fact that the quadratic variation of W is not zero. So this dt comes from the quadratic variation. When you write down Taylor's formula, the second order term is completely. It's not the order t squared, it's the order t. Cool. So lemma, let b, then f is this, so let us, if we define u of t and x equal to the expected value of f of xt, given that x0 is x. Let's not call it u equal to many things. Let's call it e. Then dte is equal to 1/2, okay, the trace of sigma square, sigma joint d to e plus d e of 0 and x equal to f of x. You see that it solves the derivative, it's a function of t and x. X is not d in general. Okay, don't get tricked by the multidimensional notation. Okay, sigma is the identity, this is just Laplacian of e. dte is the Laplacian of e plus b, the e. If there is no b, okay, this is just a heat equation.
If there is
no b, this is just the heat equation. dte equal to 1/2 Laplacian of e. Indeed, you know that the heat equation, right? So the solution of the green function is the reduction curve. Yeah, okay, so these are functions of t and x. T and x, if you want to write everything. This is the action in x. Okay, this is the differential in x. This is the x, this is x. The proof, just take the expectation and use for b. We will check a bit more closely these things for markov processes. So it's just the fact that the generator of x is this operator. Even better, take this right to this, or equivalently, dte is the operator L applied to E, where L is the operator that on some function G is just 1/2 the trace of sigma joint D to G plus B dt. So L is a linear operator acting on functions. If I give you a function, it gives me a new function. It's linear. This function is a function in C2, it's fine. then this guy solves this equation. The derivative in time is this linear operator E. You should look at this equation as follows. Just an infinite dimensional version of exponential of a matrix. Yeah? How would you write? If this is a linear operator, it's like a matrix. Now, this is a space of functions, so it's not finite dimensional, it's not a vector, it's an infinite dimensional space. But this is like a matrix, this is just a linear operator. If it would be finite dimensional, it would be an operator. So indeed, one can write here that the solution E at time 0 is F. Huh? E of 0 and x is F of x. You can write the solution formally in this way: e to the TL f of f in x. You know that if you write like the different x dot is ax, the solution writes as e to the TA x at time 0. It's exactly the same thing. And so to check the proof, let's sketch the proof. Because you take the expected value, condition to x0 equal x in ether form. So we get that E of t and x is exactly the definition of this. Then f of x0 condition at x0 equal x is f of x. Then we have the expected value of the integral between 0 and t. There, it's exactly LF fxs ds. This is a multiple. So this is 0, sorry. This is 0. Because it's expected value of the multiple. F of xt, a condition with respect to well, I take the expected value. This is exactly the definition of term derivative. I take the expected value of f of x0, this is exactly f of x. Then here, this guy plus this guy is just my operator L applied to f and computed in the point xs. Now, so I can of course take this by meaning. I can take this integral out of expected value. So this tells me that t of tx is differentiable because it's an integral in time. It's differentiable in time.
But why is it 0? Because it's some stochastic integral.
Because the expected value of a multiple, which at time 0 is 0.
And what is Martin doing? Well, Martin.
Yeah, sorry,
I see. This
So-
stochastic integral is Martin. Okay.
Yeah, this is 0. Yeah, this is 0. This is the expected value of the integral between 0 and t of sigma of EF of xs, sigma of xs dws. Given that it's 0, given is 0, this is 0. 0 is exactly 0. So if I take the derivative, I take out the that, we get dte. So of course we get immediately e0 x is f for the definition all over from here. But I also get the dt e tx is then just the expected value of LF of x. Given itself. So in particular, so for t equals 0, you get the dte computed times 0 is exactly LF, it's exactly LE times 0. If I put t equals 0, f at x is exactly e at z. These are derivatives in x. So at time 0, the equation is true. And now, either you get convinced that this is LE, in a sense, I should make commute the expected value with the derivative, which is true. I can do it, but if I want to do 10 times, what's your? So this at times is this expected value. This is up to here is square. Just let's compute it at time 0. This formula. So this is the derivative at time 0 of e. So the derivative in t of e of t and x, but computed at time 0. And is equal to these things at time 0. So these things at time 0 is, okay, LF at x0 given x0 equal x is just LF at x. L applied to F, the trace will have the trace of F, but F at time 0 is just E. So it's really our equation at time 0. Now, for Markov homogeneous in time Markov processes, this is true at time 0, is true at any time. But if you want, what I should do here is just that I should change L with the expected value. Okay? This is derivatives in x. This is integral in omega. I can exchange. This is an integral in omega. These are derivatives in x. I can just take the expected value inside L. It's informal, then say, because every time you exchange integral sum operators, you should prove it. But if I can do it, then I have expected value of xt, which is exactly E. But in reality, the clean proof is not like this. The clean proof is just to check the time 0, and then, okay, we will check the Markov properties, but basically, yeah, and so I will say some more words later to Markov properties. Or in reality, with a similar argument. I don't want to spend too much on it because we will probably later in the class we will do control of Markov processes. So with a similar argument, it is true in general. It is true. I think I gave enough. Either you think that you can exchange the integral t for you. It is true in general. I mean, if you want time 0, didn't have anything special here. So we see in general that E of t and x, E of t, let's say s plus t and x is LE at s and x. E of s and x plus t times LE plus 6 plus more, that's what you should do. It's a very similar computation done at a time different from 0. I don't want to go into details where you can do it because it's just a similar property. Check it. Cool. So this is just in the Markov processes language. This just means that this Markov process X is its generator is this operator L. Second derivative plus B, the first derivative. It's a linear operator. Now, do you know Semigroup theory. Semigroup theory. Yes? Like if you're a generator, a little bit. So. I'm a bit sloppy here. I should be much more precise. I didn't define and on what functions acts L. Yeah? And the generator, like G, I didn't say anything. Okay, C2, but C2 is maybe sigma is 0, then C1 is enough. Or so L, I'm thinking that L is an operator, but maps what functions in what function, what space in what space. Okay, I'm not being precise. Not being very precise. I mean, this for functions C2, this is just true. But so if I want to be very precise, the generator of this market process is the closure of this linear operator. For instance, in CP for L2. Well, we don't care much about this. But just to say that, of course, there is a pretty large theory for market processes, their generators. But still, so what you have to check, okay, it's two things, yes, that f of xt. So again, okay, because I erased the line again, f of xt minus f of x0 minus the integral between 0 and t of lf, or yeah, of lf. Let's do it even more in general. F of txt minus Ito formula minus f of 0x0 minus ds plus l f. If there's success, yes. This is a martingale. Let's write it more. dsf plus lf. This is a martingale because this is just the integral of df sigma beta. This is the formula. And if I call E of t and d, it's a consequence actually. If I call E of t and d the expected value of f of xt when I start to x, then this solves a PD. This solves a PD. dte. It's actually the only solution. This one dte equal to LE. E at time 0 and x equal to f. Or I can also, instead of going forward in time, I can also go backward in time. So if I fix t positive, okay, and I define g of t and x, the expected value of some function of x at time big T minus t given x0 is x. This is so when t increases, I compute here t earlier and earlier. Of course, this is the derivative in time of this is just minus the derivative of time of this. I just change the direction of time. So, or you do the same computation, or just do a change of time. So, I mean, g of t minus t and x is e of t and x. Okay. So, g, what equation does g solves? Does g solve? G solves. You know, E solves a parabolic equation. G solves another parabolic equation. Solves dtg plus lg equal to 0. G at t and x is f of x. And so let's do the following simple remark. The process zt, now this is a bit of a weird process, is g of t and xt. So I can write it as expected value f of time t minus t. So be very careful with this notation, what it means. Given that x0, xt, if we write it like this average is done on x. So,
how can you write it?
huh?
How can you write it like that?
Yeah, that's not a good notation, that's what I mean.
Okay.
So it means that it is, so let's think that y, it's better written like this, okay? Y is a process that evolves like x, okay? So, this is the expected value, because who is g, it doesn't depend who is x, depends only on the law of x, on its expected value. Okay, so that's but now I build the upper function of omega. Huh? So this is knowing that at time 0 you are in xt. This tells is the expected value of f where you are after yet another t minus t time. So if you want, it's like if a time small t you were xt, this would be where you are at time big T. Okay? So you can this it's if you want it's in reality it's like f of xt given xt. It would be more accurate, but the precise. So when in doubt, to use mathematics. Okay. So the precise way to define z is so don't get tricked. That's what I mean. Don't I wrote it to tell you not to write it like this. Okay. So g is this function and z is this process. First you build the function, then the process. Okay. Indeed, you have a very constructive way of building this function. Just as a linear PDF. With antiparabolic, what do you want more? There are countless ways. This is a very stable equation. This operator is a sort of Laplacian sigma. The trace of the trace of the Hessian is think that sigma is the identity. The trace of the Hessian is just the Laplacian. The Laplacian is your dream operator when you do any approximation scheme. If there is no Laplacian, numerically you have to add it. So you can have anything better. So the process is this. Is a martingale. Is a martingale. Is a martingale. Because this was a martingale whoever was f of t and xt. So if I do g of t, so it's the g of t and xt, so zt. Okay. G of t and xt is zt minus g of 0 and x0 minus the integral between 0 and t of dsg plus lg s xs and ds. This is just the integral between 0 and t of dg sigma divided all in xs divided. But this is 0. This is some number. So that is a math. That it is up to value 0.0 is this math. And if I compute it at final time, so I put small t equal to big T. So zt, which is equal to the expected value of f of x times 0 given that x, so no, sorry, the t is g of t and x, so therefore x f of xt. So g of big T and G of big T and X is f of X. From this definition, we already remarked. So Z at big T is f of xt. Is equal to G of 0 and x0. So G of 0 is the expected value of f of x of f of xt. Given x0. Plus the integral between 0 and 2 of bg nes xs applied to the matrix sigma xs beta bs. Cool. Every time W is a figure. So we are writing a function of xt as its expected value plus a stochastic integral. What we did do, so corollary let x be a market with dx equal to p of x with d plus sigma x beta t, and assume that there exists an equivalent martingale method Q such that Dx with sigma of x dw tilde and w tilde is a Q-running motion. So if an equivalent martingale measure exists, that's the case. And to exist, it means that you can write B as B is some L sigma. That x per x, B is in the, so this is a matrix and B is in the image of sigma. If it's a scalar, just the sigma is not 0, you can do it. And you should do, I read this, no? What you need is something like the spec to be really precise. The spec to write 1/2 of, let's write sigma minus 1 b squared. Yes, is fine. Now, if b is not in the image of sigma, what is sigma minus 1b? Okay, but beyond this technical thing, it exists. If sigma is invertible, b is bounded. These are little things. This is in red. Then consider the contingent claim or contract. Claim f of omega is just some function of x at the final time. Maybe depends on many assets, not just one. We have this mark. So now we have these Ito processes, blah blah. Now we are specifying the case where the evolution is Markov which in this case just means that these coefficients at time t are a function of x at time t. Okay. It's, we didn't define Markov, just took this expression, but I think it's more or less clear with the Markov. You have all like future and past are independent condition to the present. Okay, intuitive idea. To evolve, to tell you x evolves, I just need to know who is x at time t. This evolution wouldn't it wouldn't be Markov here. There is xt and x at time t minus 1 as well. Then this evolution wouldn't be Markov. Because if I tell you who is xt and xt minus 1, to predict the evolution, you have just more information than if you only knew xt. But if dt is just p of xt and sigma of xt, then we will check this Markov stuff a bit more in the future. But so if we take that the evolution of x is determined as a function of x itself, and the final contract you have, again, is not like an Asian option. Okay, this is a really European contract. There is a function of x time t. So there is no average of x or things like this. It's just how much the asset is worth at time t. But still, this can be a pretty bad famine. It can depend on all the things and so on. Then consider g of t and x, the solution to dtg plus lg equal to 0, g of t and x equal to f of x. Namely, but you know, this is what we use to make the computations. But what really interests us is the spectrum. Okay? This is how you actually compute G in practice. You solve these things. We have made this example where B was alpha x and sigma was beta x. Then these equations has explicit solutions. But who cares? You can make a more sophisticated model with non-linear stuff. Okay, you put the numerical schemes to find the G with the level of approximation that you want are everywhere. Okay, it's built in any computer tool, numerical tool that you can have. It's the real parabolic equation. It's really the base. It's a very stable equation. Cool. Namely, g of t and x is this. Then the price of f is well, I just apply this remark that you have here. Remember that zt is g of t and xt. And I apply it when this guy is q, is not p. I apply this formula was true for n(x), but now I apply it when this guy is q, not p, so there is no b. Okay, and this of course is my W tilde. This is true anytime W is a Brownian motion with respect to this probability, and x satisfies this equation. Okay, for q, b will be 0. For q, b will be 0. That's the only difference. But here, there is no b, as we know. So yeah, I'm sorry. So this, so with respect to q. So here, I'm sorry. LG. Here is just the martingale part. I'm sorry. I really confused myself as well. With LG, this operator without B. Sorry. Because I'm reasoning with Q. I have nothing to do with B. I'm sorry. I take G is factorial with respect to Q of this. So G satisfies this with this operator. There is no B. My apologies.
Okay.
There is no B. I applied this formula, but everything works like we made the computation in general because it's useful in general, but now we apply it to this guy. X is the same, but this factorial is Q. So this, which is just G, this is just G of 0 and X. This is the third value. Okay, is G at time 0 and x0. This equation is written antiparabolic. So yeah, you know the solution at the final time, and through the PDE you find the solution up to time 0 for each x. Then x0, you know what it is. It's the value of the stock now. So the solution at time 0 is the offer price. You can, in some sense, these numerical methods, you cannot compute it just at 1x. You compute the whole function, then you compute the value at which x is time 0. And the replicating portfolio is dg of S6S. Because look, this formula writes that F, maybe I should have, I finished the space, and either I erase here, I'm sorry, but, so, well, let's read. I don't know what I can erase, it looks like nothing. My contingent contract is F of xt, namely this guy. My favorite, now I'm considering this remark that we made before for this, for x, which is a q marking the sigma of x dw cubed. So if here this will be expected with respect to q of f of xt, knowing this 0. If you want, this is just g. This quantity was here because of g of 0 is 0. But it's exactly expected value under q of f of xt. X0 is what you know, it's the initial value of the stock. It's the moment where you buy the stocks and go to the bank. Buy the options, sorry, and go to the bank. So we know G of 0 x0 is just this quantity expected value with respect to Q of f of xt, namely what we get. And we know that it's the third price of the contingent market. So practically, how do you compute it? Solve this equation, which you know the final, which you know that it's f of x at the final time. You know the solution at the final time, and then you compute the solution. If you prefer to solve forward in time, okay, just change. You just call h of t and x. H will satisfy a parabolic equation, no? But it's the same. I mean, if xt solves something in the initial problem, xt minus t solves the final time problem. Okay, so you know f of x here. This PDE tells you how to propagate the solution up to time 0. Okay, you can think of it of this as an ordinary equation, linear equation, just it's infinite dimensional, but I don't know. Do Fourier series, make a finite dimensional approximation, then this is just an equation of the form x, I don't know, y dot equal to some matrix y time t is given. Okay? Y bar. Okay, the solution is, okay, it's backward in time, so it will be y t. Is something like e to the a t minus t Why buy? You just have to do the exponential of some infinite dimensional operator. It's a very well behaved operator. You can make all the approximations you want, but let's suppose that we can. Okay, the solution has there exists a unique and there's a nice representation, but I don't know. You can either simulate the process and approximate G, or here is more efficient to just do the numerics of this linear PD.
So it is another way to get the same result.
So it's equivalent. These two things are just equivalent. You can think that this function solves this PD, or that the solution to this PD is represented as this respective value. No, but now with respect to all the blah 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 before, where there existed some psi in which you can write contingent contact with a stochastic integral. Here, in this special case where the process is Markovian and the contingent contact is a function of finite time, I give you a very concrete and constructive way of finding the fair price and the replicating portfolio. Not before the fair price was an integral, was an expected value with respect to Q. So this is an integral of the probability space. It's still a pretty complicated object. Here, I tell you, find B and sigma that are a good model for your market. This is your business. You take the data, so you make neural net. B, finding B and sigma is complicated because they are functions. So the optimal, so you want to estimate functions. You on this to find the good B and sigmas. Okay, that could depend on B, for instance, but. You start with the market, maybe you want to enlarge, add more components to make it a good Markov model, and so on. So, but once you have this, of course, modeling in a good way, this can be very complicated. But once you have a good model, okay, you can compute G easily, really easily with numerically, at the degree of approximation that you want. You have the contingent contact at finite time, you find the solution for G at time 0, and this, at the point X, which is the current value of the stock, is the fair price of the stock. And if you want the replicating portfolio, it's just the differential G. It's a vector, the differential G is a vector. So, this is a very, very constructive way now. You make a model for the market. So if this is wrong, that's because the model of the market is wrong. Of course, then you can always complicate here and think that you can trade. Now you see that this your portfolio changes continuously in time. Of course, it's not for real. You can trade in continuous time as semi-marting. And that's okay. This has non-zero quadratic variation. Of course, this is not possible for portfolio, but this is the theoretical. This gives you the theoretical value. Then, once introduce transaction costs, you will have an interval such that if you pay in that interval, there will be no possibility of arbitrage, because there are transaction costs. So there is some. Of course, it's not precise to the. But that's a very constructive way of making a reference value for the fair price of a derivative. Derivative, so function of the original asset. Derivative is not anything. They are not derivatives. It's derivative in the sense that it's function of the original thing. And it's you can implement the degree of approximation that you want.
Some question, but not on the main topic. So if we are buyer of contingent credit for a buyer, so in some sense, do we need to know our replicating portfolio so that we can trade on the market?
No. So if you buy, you are typically if you buy, you are interested in the option. So that's it. But say that. Okay, say that for instance you are the bank. Okay, of course you will make some money because you ask more than the fair price. Of course, you are not doing your business for nothing. But then you think it's risky. Maybe at the beginning or at some point you decide that it's a bit risky. I want to. If you replicate, formally speaking, if you replicate, of course there are some transactions you cannot do with these exact things, but if you replicate, you are sort of cutting the risk of your asset, because what you do in some sense, okay, you have to pay this auction. No, I put the money now, and then I replicate the stock, so that at the final time I have okay, I replicate, say not F but minus F. So I sell you F, I owe you F, and then if I replicate it with my portfolio, at the end so I give you F, so I have minus F, and I replicate F, so I have F. Of course, I have to pay to replicate. To replicate, I have to put money. So, but at the end, I have nothing. Okay. If everybody's fair, there are no transaction costs. You pay exactly this price, and I just replicate. I gave you the derivative, and then it's my business with your money to exactly operate in such a way that I lose nothing and I gain nothing. So, okay. So then, in practice, of course, the bank will charge you something, and also will take some risks. The business of the bank is to take risk. But if at some point they decide not to take risk, they can, formally speaking, just replicate and annihilate the risk. Indeed, if you buy, for instance, if you go even to your bank and you buy some liquidity fund, so that's sort of risk-free. It's not risk-free, not risk-free, but it's like some of the safer investments that you can do. Usually they are composed by several assets. Okay, so there are some money, other public debt obligations, some money. There can be in a liquidity fund. There can be some parts that are derivatives, which are like the most risky assets in reality. So why liquidity funds? Because in reality, it's a way to compensate for. It's a way in reality to compensate the risk of the others. I don't know how to say. You can. Yeah. So that's so. I don't know if okay. This example is not good, but replicating, if you want, is a way, if you want to so neutralize the risk.
So it seems that it is useful to know how to replicate.
It's useful to know how to replicate, but also for us mathematically, if you don't know that there exists a replicating portfolio, you don't know that that's the fair price. The fair price is only inequality. So if I show you that there is a replicating portfolio, this is the fair price exists, is unique, is that one, it is both the buyer and seller price. Okay. Otherwise it would be just an intermediate value. Okay. So let's see how much time. Yeah, let's see. No, it's 7:30. 7:30. So these we have seen what to do in particular if they are linear. What was the difference in this Black and Scholes linear case? Is just that the solutions are explicit. Okay, nothing more, nothing less. but otherwise, this is the answer. You have to solve this. You should keep in mind. Then, of course, another business is you see some. Okay, you go on some market. There are 1,000 assets. Okay, maybe here you can put time, and actually, B. Could in this argument B this could not be marked really. B could depend on other things, and for the sigma does not, because we really apply to Q. So provided that here B can depend on omega, if this thing is finite, we apply this thing to this process. B, the fact that X is a Markov in the original measure P is not important. So here you really have drift. For the drift, you really have some very general many possibilities. It's just what you really want is just that this volatility part is a function of x. You could put t as well here. So, like you have a market, you have the right to add some assets, taking them elsewhere to make it good market model, and you really want to see. So you have a lot of choice to choose B and sigma, and this now, okay, you can also decide that this is not running, but the lead process. But now you are in this world now exactly where you have a lot of modeling options. And there is not an obvious kind of what do you optimize? How do you choose B and sigma? This is a pretty modern and complex problem. But what I'm telling is, once you make your choice, you can really price assets in a very price derivatives in a very consistent and effective way. This is now, all this remarketing blah blah, it's over. Here, you take the computer and you get a number, very precise. There's a very concrete way. So, so concrete that is good in exercises.
Does there exist any PDEs for markets which are not driven by ground emotions, by, for example,
Yes. For instance, a very typical. So this is it. If you think that sigma is the identity, who is the tracer? Our LF was 1/2 of the trace of sigma star d2f. So, but if sigma star, sigma joint, yeah, this sigma joint just means sigma j, sigma k. J is sum of j. Okay, and this is this matrix component I k. Just the square of the matrix in the sense that you can do the matrix and it's a symmetric matrix. But if this is the identity, the trace of the action is just Laplacian. Okay? Laplacian is a negative operator. In any space you consider it is negative operator in the following sense. For instance, in two senses, I can consider the Laplacian as acting on a space of continuous functions. Of course, you know, an unbounded operator, right? It doesn't mean that it acts on this function, it acts on a dense subset, linear subset. So, C or say RC, continuous bounded. But so, if X is a minimum, it means the following thing. If you solve lambda minus delta f equal g for lambda positive, then the norm of f is less than the norm of g divided by lambda. What does it mean that this is a negative? Why? This means that every Markov process has this property. Why this tells you that it's a negative value? You see, f, what it is lambda minus delta to the minus 1 g. So you see that the norm of f, let's write it formally. F is 1 divided by lambda minus delta g. If the norm of f is less than the norm of g over lambda, it means that minus delta was positive. Lambda minus delta is bigger than lambda. Or, I don't know, if you solve, also means that all eigenvalues are negative. If you solve Laplacian of f equal to f, this will be negative. Suppose that this is in L2, for instance, you integrate f squared Laplacian of f times f in the x. This is lambda, the integral of f squared. But if I integrate by parts the Laplacian, this is divergence of gradient. So divergence gives me another gradient here. It's minus the integration of the gradient of f squared is equal to lambda, the integral of f squared. So you see that lambda is negative. It's the ratio of minus. So all eigenvalues are negative. And in general, this is just the quadratic form of the Laplacian. No? If you think that this is an operator, this is a quadratic form AFF, where this is the Laplacian, just integrate by parts, you see that this is negative. So the Laplacian, in any sense, you consider. This is on C. This is to check. This you just check that the Laplacian over a minimum is positive, which is true. So if you take x is the minimum of g, then you see that lambda f at the minimum of g, since minus no, minimum of f. This will be positive. So the minimum of f will be more than 1 over lambda, the minimum of t. And the maximum will be less. So this tells that the norm of f will be less than 1 over lambda. So in any way you consider the Laplacian, this will be a negative operator. And this is also true for b df plus Laplacian of f. Here you have to change the measure, not important. Here is the same argument because on the minimum that will be 0. So all these operators are negative in this sense. Well, in any case, this is negative. Okay, this is a negative operator. So what I can do on the negative operator, I can do minus the Laplacian will be positive. I can do it to some power, I do the 1/2, and I do a minus. This is called the Laplacian to the half. This is what you should think. The Laplacian is like a matrix. So you take the square root of a positive matrix, you can do this. This just means an operator that if you apply, so this just means an operator that if you apply twice, you get the Laplacian. Now you have to be careful with the sign. It's either minus an operator that if you apply twice, you get minus the Laplacian. But beyond this little detail, or in general, you can do any power. Okay? So if the power is more than 1, it doesn't work. It's not Markov. It's not true of these properties. But for any power between 0 and 1, this is the generator of Markov of a limit process. So for an example is the Laplacian to the
Okay.
Okay, so instead of calling that, you can do something for which the formula will all do not with the Laplacian, but with this guy. That's all. That's all. And what we say, everything will be the same. Just this operator is not local. This is not a derivative. It's not one derivative. The Laplacian to the half in one dimension is not one derivative. It's a non-local operator. So Laplacian to the half of a function f in the point x is something like f of y minus f of x divided by x minus y to some power that depends on alpha and on the dimension dy. So the PD is a bit less, it's still a linear equation. You see, if x minus y, the more this power is close to 1, the more this integral only integrates when x is very close to y and makes at the end of the day its derivatives. But it's sort of a general, just no local derivative. Okay, the answer is just yes, just you have here a different linear operator.
So in one dimension, we will have non-derivative, but some fractional derivative.
The derivative, you see, minus this, yes, a fractional derivative, but minus the derivative doesn't satisfy this again, to the half, because the derivative is not positive, it's Q-symmetric. Integrated by parts is just a minus. So minus the derivative is not positive. It's not true. But these correspond to making some jumps if you look at the process. Like the Laplacian corresponds to Gaussian things, this operator corresponds to the jumps. But it's the same. Cool. But coming more in our context, yeah, maybe since we are discussing this, they can just finish. The time is over. Even we start a bit late. So yeah. So let's just close this chapter here, and let's just come back to a moment of what are Markov processes. So. A homogeneous Markov process. So let's completely erase everything and let's just remark an introduction to Markov process. The basic idea is that if I have a process xt, okay, I can go and the function f. I can do something like the expected value of xt. If I know there was an x. And this is usually denoted expected value when I start in x over x. Now, the Markov idea, not every process is Markov. You think that the process is a homogeneous Markov process if I know that there is the following, that if I know that I start in x at time 0, and then I look at the law of the process at time t, so going from 0 to t, on the one hand, so it's the same as going, say, from time s to time t plus s, and additionally, in the following sense, in two following sense. One is that if I do, writing a expected value of a function is just a way to characterize the distribution. If you know the expected value of all functions, it's a way of saying you do the distribution. So if I do expected value of f of t plus s given f t, given xt, this, on the one hand, I want that this is the same thing as f of x at t plus s, knowing x at all times before t. So that's the Markov property. So if you tell me what happened up to time t, and you want to make a prediction on the distribution of x at time t plus s, that's the same. Being a Markov doesn't mean to be in this context Markov process. That if I give you xt, only the value at time t, not all the history of the thing, only the value at time t, and then you make a prediction on the distribution at time t. So the conditional distribution at time t plus s, knowing all the xt, is the same as the conditional distribution at time t plus s, knowing all the history up to time t. So this means that sometimes this is saying that the future, the past before t and the future are independent conditionally to xt, to the present. Think of the market, okay? If you want to predict the prediction, the process is Markov. The prediction you can do, knowing where the asset is today, the value of the asset today, has the same accuracy as the prediction you can do, knowing all the history of the asset. Now, in this constants of the market, every process, not every process is Markov, but kind of adding enough variables, you can make processes very often Markov. Because suppose that your prediction depends on xt, but also x at t minus 1. Then instead of considering the process xt, you consider the pair xt minus 1. Now this will be Markov. Okay, so up to losing dimension, very often you can make a process that, after increasing the dimension, you can make a process that was not Markov, a process that is Markov. This in general is a big word which was more fashionable a few decades ago, but like how to find Markovianity when it's not applied. But okay, we, just for the sake of simplicity, because if up to adding variables, we can also make non-homogeneous Markov process, homogeneous, so we can also think that the expected value of f at time t plus s given x t. So this is just the Markov properties, but we can also think that this is equal to the expected value. So let's write this. Given that xt is x, it is the same as the expected value of f of x s given that x0 is x. So how much you change between time t and t plus s doesn't depend on t, only on the time increment. So for instance, if I do something like this is a Markov process. But it's not homogeneous. To make it homogeneous, I have to do that this don't depend on time. But again, if xt is a Markov process that is not homogeneous, the pair txt, this will be an homogeneous Markov process. So when we do all the mathematical formalism, there is no need to. It's like, if you consider a node E, x dot equal to b of t and xt, you consider yt equal to the pair txt, then y dot. Okay, one of the components is just 1. So it will be f of yt, where f of so yt is txt is the vector 1 b of t and xt. It's exactly the same. In ODE, the differential equation is a Markov process. So, homogeneity, that there is no loss of generality. So what's cool about Markov processes is that if they are regular enough, there are plenty of ways to characterize their law. So in this case, you see, I can define, so for a Markov process, define a semigroup, so an operator. Let's say that on bounded measurable function. So you just define STF, so F is a bounded measurable function. You can define a new measurable function, STF, at x, which is just the expected value of F of t, knowing that x is x. This property tells you this is a semigroup. S0 is the identity, and ST. If I apply ST to SS, so for each F, I take F, I do SSF, this is a new function. I apply ST to this new function, this is ST plus S. So STSS is ST plus S. And then, so it's the same thing to have the Markov process, the law of the Markov process, or have just this semigroup. They are the same because, okay, if I have the probability measure, the law of x, I build this guy. But if I have this guy, I can build the finite dimensional distribution of the Markov process. So I define, so converse, so define operator. At the same time, so conversely, let's do this. What property is this? ST is identity, ST plus S is this. What other property has this ST? This has the property that ST of constant function equal to 1 is 1. Because the expected value of constant is the constant itself. And there's other properties in reality. If F is positive, preserves positivity, STF is also positive. And is this enough? It also, no, if F is less than sum is bounded by a constant, STF is bounded by the same constant, but I think it's a consequence. So, yeah, because the expected value is something positive. So, what I can so given conversely, given a semigroup ST satisfying let's call it A, B, C, D. There exists XT Markov such that STF is equal to So for each x, I can build the stochastic process which is Markov starting in x. What do I have to do? I just have to build the fundamental distributions. So, okay, the fundamental distribution times 0, it's easy. It's just the delta mix. But then let's just, how should I create mu, for instance, 0 and t? Okay, so the probability, let's say, of A times B. So the probability that x0 is in A and xt, for instance, is in B. I have the semigroup. These I have to define, but it wants to be distinct. Well, of course, this is just one if this initial point is in A or not, and then I do st1b in X. I'm right. Okay, x0 is in A is an empty condition. If it's not there, and so xt is in B. Probability xt is in B after the fact that I start in X. This is like the expected value of indicator function of B xt intersect with the condition x0 is X. Then I do three things. Okay, I have to do the probability that x0 is in A1. Let's write x is xt1 is in A0, xt1 is in A1, xt2 is in A2. And then this I do the following. I do s t2 minus t1 indicator function of A2. This is a function. I apply to it I apply this to st1 minus 0, 1, A1, then indicator function of A0, X. Then if you want to do all the fundamental distribution, you iterate this in a very long formula. You want me to write it? Or, so if you want to do expected value, no, if I want to define mu, okay, 0, T1, Tn, I take them ordered this time. Offsets A0, A1, An. It's just my definition. You give me the semigroup, I define this thing. I define this. 0, unless the point where I want to start is in A0. Okay. Then I define st1 of ya1 st2 minus t1 of 1a2 stn minus 1 of 1. It's a complicated index. It's a complicated formula, but it's not create out of nothing, it's just you condition every time. So you want that this is the Markov property. So this is the Markov property. So you condition it at ft1, ft2, and so on, and every time use what the Markov property should have to come to this formula. And then you use the opposite way. So if this is what you use as a definition, and if you do, it's not hard to check that this satisfies Kolmogorov extension theorem. And so this property is so there exists a law on the space where X is defined, where the ST is defined, of a stochastic process. So there exists a stochastic process. I'm not being a bit quick. I'm just saying, if you give me the semigroup, I know, if I know x0, I know how to evolve to compute the law of x1. If you give me x0 and x1, I know how to evolve to compute the law of x2, and so on. I can put this in formula in just one line, which is, you just look at the formula, it's not understandable, but it's just due to conditioning. you can check, if you remember, there are two conditions for Kolmogorov transition theorem. One is the computability when you permute these things, but this is defined automatically because they're defined only when these times are ordered, so when they are non-ordered, they're defined by computability. And the other is that if I remove one of these AI, then I get a distribution with one index less, and this is just this property. And this fact, I just needed to make it possible to say that I want the probability, this must be positive. So this must be a positive function. On all these indicator functions, that
It indicate a function of A0 and what is an argument?
So I think, look, just look when there are two, okay? It's ST1, ST1 applies to the new function 1A1 applies to the function ST2 minus T1 A2. Then if there are three, here I just put also 1A of the previous time and I apply ST. Every time I just, this is like the probability that you finish in A2, okay? Once you have evolved up to time T1, just evolve for another time T2 minus T1 and impose that you are in A2, and so on. So every time it's S. So at every step you put a function and a time evolution. We never use this property. It's just that it's giving ST is the same as giving P.
And how is the initial point X imposed?
For every, you have to do this for every X. So in reality, what you do, yeah, is that for every X you build this probability. The Markov process that starts in the point X. Now, so okay, let's stop it here. But what we want to do next is really optimization. Okay, so what was in all these things we did in arbitrage theory? One of the problems is that we think that there is a market and we operate. And remember we discussed it a couple of times ago the squeeze problem where this doesn't really work. What we do influence the market. Okay, that's the main limit of these things. What we did, it's good if we are small player in a big pond. But once, and this is often the case, actually. For instance, once the value of derivatives starts to be comparable, even exceeds the values of the original assets, how can one think that you operate and it doesn't change? Of course, it does. There was this very famous example of this short squeeze that we discussed on the stock GameStop. You remember we discussed this, that where the value on the a lot of hedge funds have shortened this stock. So, but for a value that exceeded by several times the actual capitalization of the company. So somebody noticed it and they started to buy shares of this company because at some point these hedge funds actually had to buy the stock to honor the derivative that they had sold. Okay, so they had, for instance, maybe they did something more complicated than this, but they had like they thought that the company would go bad, which it was. The prediction was correct. The company would go down from their operational point of view, the real economic part. So they, somebody for a very large amount of money, took some money in change for the right in maybe 1 year to sell you a stock, many shares of this stock for a given price, maybe $20. So since they were expecting the stocks to go below $20, They would think that they take the money today and give you nothing tomorrow. But what is the problem is that they didn't do for one stock. They do it for a value, for one share. They do it for a value of, so the number of derivative contracts exceeded by, maybe a few times, the total number of shares of the company. So this means that you could buy shares of the company, even if this company is doing very bad business, you buy the shares of the company, this company goes very high in the price because you are buying, and tomorrow he has to buy all these shares and give it to you for $20, and the shares are $500, however. So what is the problem? The problem is this guy is an hedge fund. They saw, they do some very accurate prediction, very accurate model. Okay, of course, in reality is that they were trying to make money, and the traders are not so naive. The problem is really that the hedge fund gives their business to traders, and traders, they do their own interest, not the interest of the hedge fund. So they take a lot of risk, because if you get risk, you make money. If you don't, they fire you to change company. That's the main problem. But so you always take more risk than need. But beyond this, like the rationale, if you do it on the computer, what was the problem? Is that you make a prediction, okay, the X behaves in this way, this is very accurate, and indeed you are right, that you understood, you got some information, maybe you made some also economical prediction, and they understood that things were going bad. They make the right prediction. But once your interaction with the market is so enormous that it also takes an impact on what the market does, exactly, because if you, okay, it went below the strike price, it should have gone. But somebody noticed that you bought so much that they legally increased the price of the, they just bought it. They just bought it. So you see that why this value went up, of the value of the share? Because you bought the derivatives, or you sold the derivatives. So it means that what the operator does has an impact on it, on the value, on the stock. This is not true. I mean, if the value of the amount of money you use is very small with respect to the capitalization of that particular asset, it's not true. But for this huge amount of money, it's true. So now, you think what would be the problem is that, I don't know if you think that this is the X, okay? This is a function of what you do, of your portfolio. Okay? So a standard way to model this kind of problem is that of controlled Markov processes. There is a Markov process with a generator, nice things, but depends on some parameters that you can control. This is not this. While the arbitrage theory is born in finance, this is not born in finance. This is born in really control and optimization theory. You want to send Apollo 11. What was landed on the moon? I don't know. You want to send a spaceship on the moon? Okay. Then it's a Markov process. There is noise. It's inevitable. You cannot fire from here. You fire exactly in the direction of the moon and never control anything anymore. Such a precision doesn't exist. Okay. You have to continuously fix a bit the orbit. There is noise and so on. So the position of the space shuttle follows exactly Newton law with some noise. Okay, in this case you will have some observation, and you have to choose the theta in that case such that at some actually stopping time you are on the moon. Okay, so if you want to minimize a function which is 0 on the moon and very big if you finish elsewhere. Okay. Here in the finance, you optimize the utility of the money you have at time t, or the utility of the amount that you consume, and so on, the dividends that you give back to the shareholders. But so it's a bit of a different thing now. You are not so it's two different problems. Yes, you want to price a derivative. And this, I think, we understood in a very large generality what to do, and make some, I forgot, maybe you can try. You can try to understand what to do for the prices in this binomial model, this one with every time you go up or down, that we discussed at the beginning. I forgot to tell you. You can try to work it out by yourself.
work out what exactly is model.
How to price it?
How to price it.
It's the same as what we have done here. This is a Markov, it was a Markov process, and it's the same procedure. Maybe we can discuss a bit more, estimate yourself Markov processes. But maybe next time we can do some exercise. But then this is the next thing. So this is a different thing. There is no option to, there's no derivatives to price. I don't have to quote you the exact price of a derivative. It's a different price. I want to, I'm a trader for a bank, and I need to optimize some. I make again, making the model is a different business, choosing B and sigma. But I want to then, given this, I want to optimize the utility of the money I make. And we have discussed these things that you don't optimize the money, you optimize the utility of money. But you remember these things, yes?
I don't remember.
I mean, what you try to optimize is not the amount of money. The amount of money you have at time t will be, it's a random variable. So the typical thing people optimize in these models is the expected value of some concave function of the amount of money you have. Because I think it's quite clear that you prefer to have $1 billion than to have 0 probability 1/2 and 2 billion with probability 1/2. The expected value is the same of what you have, but of course, with $1 billion, you're much happier than 1/2. So that's true also for a bank. Okay, for the bank, this function will not be as concave as for a single person, but it's okay. You optimize something, it's not running cost and so on. This is a much more Markovian theory. In the previous example, general theory, you want to do computations, okay, Markov case, okay, make things Markovian, and you will have a very constructive way of calculating things. And here, at least, yeah, here, the nature of the problem is really Markov. So this is just very, okay, this is just, knowing this semi-group, this is like the solution of the PDE. Is the same as knowing the law of the Markov process, and then we will check a bit quickly other things. I can give the generator. There are many different ways to give to assign a Markov process. Resolvents, generators, semi-groups, probability measures, martingales. They're all more or less. These two are good. Okay. It's a lot of stuff, yeah. I don't know. We can take we can take one lesson to review the points of view. I don't know.